Is asking, write a code fragment which sets PA5 high, delays the MPU exactly half a second with a 4 megahertz external oscillator, and sets PA5 low, delays another half a second and repeats using only instruction delays. Use subroutines. Okay, now let's see how to do that. And here what we have, the provided one is 4 megahertz. That's extra provided to be 4 megahertz. Megahertz, and e clock is 1 over if you divide extra by 4, that is e clock, because the relationship between e clock and the extra is 1 over 4 times extra divided by 4, and that's gonna be 4 divided by 4, that is 1 megahertz. Okay, so currently we have 1 mega is 10 to the power 6, so 1 million cycles per second. But in this question it is for the half second, so it's going to be half of it, that is 500,000 cycles per half second. Okay, this is how many cycles we had to achieve. We had to write a code to achieve this many cycle. And also the question mentioned that set the PA5 high and PA5 low. In order to do this one, you have to know one thing, that the port A has a range of PA7 to PA0. You know, sometimes the question may ask, set the PA4 low, PA4 high, PA5 high, PA5 low. So based on that, you have to decide what value you're going to load. In this case, this is PA5, so the equation is basically you have to put the power of that. So since this is PA5, you have to put 2 power 5 and 36. This one comes in the code like you have to load with 36 in 36 in decimal, and if you write this one in hexadecimal, that is 20. Okay, because if it's in the second place, each letter represents 16. Like if it's 10 16, 20 32, and so on, so it's going to multiplication of 6 times. So 20 is the hexadecimal. You can either write in hexadecimal, binary, it doesn't matter, but you have to make sure you are loading 36 decimal value in that. So that is one thing to remember. And then another thing we have to know is we have to know each instruction costs how many cycles. So let's mention that one here, the number of cycle for instructions. And here LDAA and STAA, both of them cost 4 cycles each. So LDAA 4 cycles, and then STAA, both this also 4 cycle. Okay, and then LDX, this is load to accumulator. This is load to accumulator A, store into accumulator A, and this one is load to accumulate load to index X. That costs 3 cycles. And then NOP, this is just for the delay. This does nothing, but in case you don't need 2 cycle delays, you can just put this one. And then we have JSR, that is jump to subroutine, that is 5 cycles. and then RTS, that is return from subroutine, that is 5 cycles. We are interested in subroutines because in the question is mentioned use subroutines. Okay, only instruction delays, use subroutines. So we need to use this subroutine instructions. Okay, and then we have few more as well. Like we have B and E. This is to create the loop. This is gonna help us to branch if not equal to 0. So we can branch something until it becomes 0, and it costs 3 cycles each time. And then DEX, this is decrement of index X register, that is 3 cycles. And then we can also BRN, use BRN and then asterisk, that is for the 3 cycles delay. Okay, this NOP and BRN is gonna help us to adjust. Like let's say we are gonna use all these, right? All these, and if we couldn't get a value that is gonna complete the cycles required, then we can use this NOP or BRN or both of them based on how many cycles required. So if we can use them and minimize the process, that will be helpful. But it's better to put this one as minimum as possible, these two. That will, in that way the code will be very effective. Okay, now let's go and write our code. So first we have a start, and then the question is saying that set the PA5 high and then PA5 low. So to set that one, we had to load accumulator A with the values. In this case PA5, we just found out that is here, that is we should load with 36, that's 20 in hexadecimal. So to load 20 in hexadecimal, you just put the $sign, number signs for to represent we are loading a number, and then a $sign for the hexadecimal, and then 20. Okay, and this is gonna load 20 to set PA5 high, not PA4, PA5 high. Okay, and then we had to store in the accumulator A, and that should be stored in the port A. And then JSR, this is jump to subroutine, and the subroutine we are going to have is delay. We are going to create this one later on. And now we have, this is PA5 high and PA5 low, that is always 0. It doesn't matter what PA you have, like you may have PA4, PA3, PA6, whatever. The high, that's the one you have to calculate based on 2 power, but the low is going to be always 0. So LDAA, and then here this is going to be just 0. And we just represent this one in 8 bits because this accumulator A only takes 8 bit at a time. So that's why hexadecimal, if you are representing this one in hexadecimal, you have to use 2 digits because each digit in hexadecimal is 4 bits. So you can only use 2 digits. Or if you are using a binary, then you have to put a percentage for the represent binary, and you have to put 8 bits because each digit of binary contain 1 bit. So you have to use 8 digits to represent. So in the same way you can represent binary as well. Like in binary, if I represent this one 8 bits, okay, I had to put 8 numbers, and you know that in binary the first digit take the ones weight, 2, then 4, 8, 16, 32, then I need 30. According to the calculation, I need 36 here, so I need a 32 and a 4. So the number I should be loading here is, I have to have 1 here and 1 here. So 1, 1, and make sure it 8 digits as well. 0, 0, 1, 0, 0, 1, 1, 0. You can put a percentage and load this one as well instead of this. Both way it works. And here you can put 8 zeros if you put percentage sign. That is for the binary representation. Okay, same thing. And then here LDAA, and then store, the other part remains the same. STAA, here we put port A, store in the accumulator A, and JSR jump to subroutine, and the subroutine is delay. And then we put a BRA statement, that's branch always, to start. Okay, and then now we are gonna have the subroutine that jumps to that delay here, and in this one we are gonna load X, index register X, and this is, here we have to put a number. Here you know you don't have to worry about whether you're putting in hexadecimal, decimal, or binary, whatever, but it's better to put in decimal because that is very obvious, you don't make mistake. Okay, this one doesn't matter, you can put anything here for the number. And then so this is for the how many times it's gonna run. Now I have to continue and complete the coding. I don't have space here, but you know it should be top to bottom, but I'm writing here since I don't have space here. So the after this, the one below this is gonna be a loop, and we are gonna create. So I name the loop as, I erase this one as well, erase this one, and the name you are giving for the loop, you can name anything. You can just name it loop 0 or any name you decide. I'm just going to name it as delay 1, and then here we do the decrement ex. This is decrement of index register X by 1 each time, and it's going to cost 3 cycles as we seen before. Here we have seen all the cycles required. dx costs 3 cycles, and then we are going to have a BNE statement. This is branch not equal to 0. It's going to keep on branching until the number we put here becomes 0. Okay, and this one also requires 3 cycles as we looked at here. Okay, and then there are 2 instructions you may have to use based on if it's giving the, like, let's say you're doing this, you're putting a you're putting a number and you're doing this, and if it doesn't satisfy the cycles required, like the cycles we need to derive is 500,000. This is the cycles we are trying to achieve. If we cannot achieve with this instruction, then we have to use these two, NOP or BRN, or both of them, depends on how many we need, but we can decide that one later. And then RTS at the end, that is gonna take 5 cycles. This is a return to subroutine since we are using subroutines here. Okay, so let's look at the cycles each of them are taking. As we seen here, LDA gonna take 4, STA gonna take 4, JSR takes 5 cycles, and if you see the one we are taking related to subroutines taking 5 cycles, JS and RTS. So this one taking 5, and this one also taking 5, and here again 4, 4, 5, and then this one doesn't require cycle, and this one LDX taking 3 cycle, and this one 3 cycle DX. Okay, and then BNE takes 3 cycles. So the easy way you can remember is, you know, if you're loading or storing accumulator A, it's going to take 4 cycles each of them. And if you are dealing with anything related to subroutine, JSR or RTS, that takes 5 cycles. Other than that, all of them take 3 cycles, and the extra things, if you want to add, NOP takes 2 cycles, BRN takes 3 cycles. So that's the easy way to remember. Now the things that's gonna occur only once is these things. Okay, let me point out all the things that only happen once. This one only happened once. Okay, this one only happened once, and this one also happened once, and this is the loop. And here I have to mention delay 1 as well, because it has to loop back to delay 1 until it this number becomes 0. I put the loop name here, so it's going to keep on looping here, and this is the part that's going to keep on repeating. Okay, that's going to cost 6 each time when it repeats 6 cycles, and this one only happened once. So let's add all the things that happen only once and subtract them from the 500,000, so we can decide what is the value we load here. So it's gonna fill up the rest of the numbers. So here, if I calculate this one, 4 plus 4, that is 8, 8 plus 5, 13, and then again here also 13, so 26 total, and then 26 plus 3, 29, 29 plus 5, that is 34. So 500,000 minus 34. Let me use a calculator for that. I'm using a calculator. And this one, 500,000 minus 34, that gives me 499,966. Now the next thing is we have to divide this one by 6 and see if we are getting a whole number. If we are getting a whole number, then we are good. We put that whole number here and we are done. But if you are not getting whole number, then we have to decide. If I put which one, that will give me whole number. If I put a knob, that will reduce 2 cycles, that will make this one 964. Then divide by 6 again, see if it gives whole number. If it doesn't work, then try this, minus 3, divide by 6, does it gives whole number? If it not, try something. But one thing for sure, if you divide an odd number by 6, that's not gonna give a whole number, so we can avoid doing this one. Okay. So now I'm subtract, I got this one. Now I put this number and divide by 6. Let's see, 499,966 divided by 6, that is not a whole number, that is giving me a fractional number, so this one doesn't work. So now I have to add either a knob or a BRN. Let's try with a knob. So if I add a knob here, it should be added after the loop because we need to minimize the instructions. So it's better idea to write it right here. So it's gonna just take 2 cycles. So if it takes 2 cycles, then now this one becomes 36. The things that only happens once. So this is gonna turn into 64 right now. Now I'm gonna divide this one by 6. 499, 964 divided by 6. That is a fractional number. So again, this one also not working. Then the next step, should I use this? It's bad idea to use odd number when we are dividing this one by 6 because it's not gonna give a fractional number always. If you divide a odd number by 6, that's gonna give a fractional number. So I'm gonna neglect this. The next possible even number, that is if I add one more knob, that's gonna be taking 4 cycles. So I can do that here. So I put the RTS below, I erase the RTS, put another knob. That's gonna consume another 2 cycles. Now I put RTS, that's 5 cycles. Now I'm if I do that, then the things that only happens gonna turn into 38 right now, and this gonna turn into 62, and then I divide this one by 6. 499,962 divided by 6, that is giving me a whole number. So this one works. So we stop there, then we put the number that is coming out of the calculator, that is 83,327, and that's that many times this loop has to be running in order to give this desired value. Now if you add all of them, like 4 plus 4 plus 5 times 2, because it's happening twice here, and then plus a 3, and then plus another 3, and then okay, these 3 plus 3 happening this many times. That's the reason we are decrementing, because each time it decrement by 1 until it becomes 0. It's going to keep on running. So this 3 plus 3 going to happen on this many times. So 3 plus 3 times 83,327, and this comma is not necessary. 83,327, and after it finishes that, then it's gonna do 2 more knobs. That's 2 plus 2 and then 5. If you add them together, then you should get 500,000 back. Okay, you can verify that by doing that. Like, let's do it. So first 4 plus 4 plus 5, that is 8 plus 5, 13. 13 times 2, 26, and then plus 6 times 83,327. Let me do that first so I don't make a mistake. 6 times 83,327, that is 499,988. Okay, let me double check it. It doesn't make 6 times 833,000, 83,327. Okay, 499,962. Okay, then plus 26, then plus 4 plus 5, plus 4 plus okay, I neglect the 3. I had to be loading here as well. There's another 3 loading X, so plus 3, because currently I'm getting 499,997 plus this 3, then that is 500,000. So that is adding up perfectly. Okay, this means what we done is right, and that's it. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you